if you're watching this, you missed day 2 of our week 8 Foundations of Tech lecture. Let's get going. So first of all, really important housekeeping. As you can see, a bunch of assignments are nearing their deadline. Also, spring break is coming up, which is an ideal opportunity for some of you to catch up. So please be aware. Assignment 7, the deadline is Friday, March 26th. Assignment 8 and 9, the deadline is going to be April 6th. That's the day after spring break. So please make sure you complete these if you need to. Additionally, if you have any assignments that are past deadline, as long as you turn in something, I will give you at least 50%. So please turn in something so I can give you credit. So highly recommend. Today we're talking about forces on structures. So this is a really cool idea to consider. And that is, what kind of forces are there in play when we talk about structures? And what kind of material should we make our structures up, and what kind of shapes should we use in order to best counteract these forces? So let's get going. First of all, when considering a structure, there's all kinds of things that might be a good material to use, and others that might not be, depending on what kind of forces you're dealing with. So for instance, wood is not particularly sturdy if you use it to make lateral members, but are very good at vertical ones. But you can be clever about how you use wood, and it can then be used in a number of different ways. So ultimately, why is it better in certain configurations than others? Well, it all has to do with the 4 fundamental forces that buildings and other structures have to deal with. So you have your shear force, which occurs when 2 parts of an object are pulled different directions. Think of this like chopping wood, right? If you chop a log into 2, as it splits into halves, what's happening is it's shearing, and one part is going one way and one part's going the other way, and it's splitting in half. It's the same thing occurring here. Usually this is bad and we want to avoid it. Torsion is when something twists. Compression is if you were to squeeze your 2 hands together, you'll experience some compression. And tension, if you will lock the fingers like this and pull apart, you'll feel some tension. So how do we see all of these? Well, there's a, before we took a look at that actually, there's 2 other dimensions to this, and that is dynamic or live versus dead, static loads. So a dead load, or the static load, is something that is the weight of the building itself. Something that's already present and always the same, doesn't change. Whereas live loads are something that might come and pass, or might change over time, or could vary. Something like the wind is a dynamic load. You don't know how much wind you're going to experience necessarily all the time, but you can estimate it and you can account for it. And similarly, weights of cars and things like that. So as I was saying, to really get a picture of how these tension and compression forces, for instance, work within a building, I highly recommend you watch this video. It's posted in my PowerPoint on my MCPS. I'm not going to play it for you. But the gist of it is, as you see here on the diagram, there's many parts in a building that are constantly under some kind of force that's creating compression and tension, and in clever ways you can balance that out and prevent this force from being an issue. If you have a board placed across 2 beams like so, the top of the board is going to experience compression while the bottom experiences tension. Now certain materials are really good at withstanding something like that. For instance, steel rebar is very strong and will not usually buckle unless there's a lot of force. So a very popular material is reinforced concrete, which is steel rebar with concrete poured over top of it. This allows something that is both very strong if you push on it straight down, as well as from the sides. It withstands a lot of pressure from every direction, and is a good member to use vertically or horizontally. So that's quite nice. Unfortunately, it's a little bit pricier than something like wood, so oftentimes wood is good enough, but if you're building a really large, really expensive building, reinforced concrete is the way to go. Alrighty. So there are, of course, many mistakes that have occurred over the vast number of years that humans have been building things. This is a famous one. This is the Leaning Tower of Pisa, of course. And this is just an example of something that could be hard to account for. So here, the engineers did a good job accounting for the dead load, the live load. All of that was figured out, but what they couldn't account for was the ground settling unevenly underneath the building. So even though the building itself was technically a sound design, as it settled into the foundation itself settled in a slightly askew way. So just goes to show there's always more things to think about. And now we do ground surveys to make sure this doesn't happen. This is a short video, I highly recommend you watch it, about a skyscraper that was built in Boston, but they didn't account for thermal stress. Again, what is thermal stress? Well, this is something that occurs when you have changing temperatures, and the glass that they used would expand and contract under those temperatures in a way that they didn't account for. And essentially all the glass panes from the skyscraper would pop out of their frames and fall down hundreds of feet below and shatter on the sidewalk, which is of course terrifying for the passerbys, but also disastrous for this company as they had to replace every single window in the skyscraper. So again, lots and lots of unpredictable factors. And last but not least, this is the Tacoma Narrows Bridge, which was vibrated by the wind at just the right frequency where it started oscillating. Highly recommend you watch this video. It's very, very fascinating. But eventually it did lead to disastrous results as the bridge collapsed. And now we take into account to make sure that the bridge doesn't resonate with the wind this way. So all of these are examples of unpredictable things, but now that we've seen them once, we have experience and we can account for them. So building engineering is a very vast field. There's a lot to keep in mind, but ultimately just accounting for live and dead weights is a lot, and we're going to try to kind of do that as best we can in some simulations coming up. Please make sure that you complete assignment 11 by midnight on Friday, and that's materials exploration from last time. If you missed our previous lecture, you need to complete assignment 10. Assignment 12 we were going to do, but unfortunately the website that I was going to have you use to practice building a bridge does not work for everybody, so it would be unfair to have some of you do it and some of you not do it, so we will work on an alternative, and we'll do that after the break. Thank you guys very much. Once again, if you have any questions, please make sure you email me, and I hope you guys have a fantastic break. See you later.